So these are the remaining 5.3 notes. We're going to start with tree diagrams. So it says the general multiplication rule is especially useful when a chance process involves a sequence of outcomes. In such cases, we can use a tree diagram to display the sample space. So what does that mean, a sequence of outcomes? So that implies that there's some sort of order, like one thing happening after the next. So if we think about, for example, tossing a coin twice, the sequence of outcomes comes from the result of the first toss, followed by the result of the second toss. Okay, so let's try to understand what's going on with our coin toss situation. So when we start with the tree, we're going to start right here at the beginning. So that's our scenario. We're going to toss a coin. And then as we move down the line, like each branch, so we have our first event, which is our first toss. And you understand it could go either way, right? It could go heads or it could go tails. There's a 50-50 chance. So probability 1/2 on this branch for heads, 1/2 on this branch for tails. Could go either way. That's our first event. So that's almost like our first level or our first layer for this tree. And then our second event is our second toss. So that would be event 2. So now you can see how this thing starts to branch. So let's say we get a heads on the first one. Our second toss, we could still go heads or tails. So there's another level of branches here. Same thing if we get tails, we could go split that and go heads or tails for our second toss. So we're interested actually, what's the probability of getting 2 heads? We're going to flip the coin twice. That's why we got this tree here. What's the probability of getting 2 heads? So I actually want to map out the route on this tree. So we start with tossing a coin. To get 2 heads, we obviously had to get a heads on our first toss, so that would be right here. So I'm going to shade that in. That's the first part. And then we have to get 2 heads, so that means the second layer, the second event, I have to choose heads also. So I go heads and then heads. So what's the probability of getting 2 heads when I flip a coin twice? So probability of 2 heads would be 1/2 times 1/2. So I'm actually just multiplying down each branch. As long as I have my route mapped out here, first level, second level, I'm multiplying down the branch. So our answer, 1/2 times 1/2 gives us 1/4. And you probably knew that already, right? What's the probability of getting 2 heads in a row? Well, the sample space is actually pretty small, right? You could only go heads, 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 tails, tails, heads, or tails, tails. So there's only 4 possible outcomes. So you might not have needed a tree for this situation, but this is like a nice example to start to acclimate us to when would we ever use a tree. They're actually really handy, especially when we have more than one event going on in succession. We just map out our route here, and then for our answer, we just multiply down the branches. So this would be 1/2 times 1/2, so the probability of 2 heads would be 1/4. So me personally, I'm a big fan of making probability trees. They seem to help immensely as far as us just being visual creatures and seeing what the outcomes would look like, and then we just have to multiply down the branch, whichever way we went. It's definitely not absolutely necessary to make these things in every situation, but it's definitely a tool that we can use to help us solve some probability problems. So let's look at example 3, late for school. I really like this one. It says, Shannon hits the snooze bar on her alarm clock on 60% of school days. We've all been there before, right? If she doesn't hit the snooze bar, there's a 0.9 probability that she makes it to class on time. That's great. However, if she hits the snooze bar, there's a lower probability, believe it or not. There's only a 0.7 probability that she'll make it to class on time. So Shannon is faced with a couple life decisions in the morning, just like we all are. One of them is, should I hit the snooze bar or not? If she doesn't hit the snooze bar, she decides to get out of bed, she's way more likely to make it to school on time. If she hits the snooze bar, she's less likely already. She goes from 0.9 to 0.7 probability of making it to school on time. So let's start with actually making a tree diagram here. Why don't we put Shannon at the base of the tree? And then her 2 choices when she wakes up in the morning. So the first event, she can either hit snooze or she can go no snooze. And so I need to put some actual probabilities on these branches right here. And this is not where we would put 0.9 and 0.7. That has to do with the odds that she makes it to school on time. This actually goes with the 0.6 or 60%. it says she hits the snooze bar on 60% of school days. So snooze would be 0.6, and then not snooze would be 1 minus that. So 60% of school days she hits the snooze, that'd be 0.6, and then we can do 1 minus that to get 0.4 for her not hitting the snooze button. So that's our first event. It's done. It's in the books. The next thing she has to do is, well, she's either going to be late to school or not. So our second event, let's branch off this one. Event 2, she's either going to be late or on time. So there's a chance for her being late or on time for both cases, whether she hits the snooze or not. And then if we read the problem here, it says if she doesn't hit the snooze bar, so no snooze, there's a 0.9 probability that she'll be on time. So we can put 0.9 from no snooze on time. That gets 0.9. Well, that means that she doesn't hit the snooze. What's the probability she's late? Well, that would be the leftover. 90% on time, therefore 10% late. So that would be 0.1. And then there's a 0.7 probability that she makes it to class on time when she hits the snooze. So now we can look, okay, hit the snooze button. She only has a 0.7 probability of being on time. So we can put 0.7 there, and then the leftover from that would be 0.3 for her being late. So there we go. There's our tree diagram for Shannon and her morning decision whether to hit the snooze or not. And we have the probabilities whether she'll be on time or late given the decision from event 1. So part B says on a randomly chosen day, what's the probability that Shannon's late for class? So this question doesn't care whether she hit the snooze or not, right? It's like me being the teacher. I don't care what happened before you got here necessarily. I have to mark you late if you showed up late for class. So what's the probability she's late? There's 2 different ways she can be late here. So probability she's late. She could either hit the snooze and be late, or she could go no snooze and be late. So we have to count for both of those. So the first one, she could go snooze button and be late, or she could go no snooze and still be late. Notice I'm using the intersection symbol. So late and snooze plus the other case, late and no snooze. So let's start with the first case here where she's late because she hit the snooze button. So we can just go right down the route here, right down the tree. First layer, she hit the snooze button, and then she was late. So we've got 0.6 and 0.3, event 1, event 2. So the probability she's late and hit the snooze button would just be 0.6 times 0.3. So we multiply down the branches. That's the first case. That's taken care of. How about the probability she's late and she didn't even hit the snooze? That's unfortunate. Didn't even get to sleep in, but she's still late. There's still a chance that that can happen for her, right? So the probability she didn't hit the snooze and she's still late, let's go down that route. So that'd be the orange here. No snooze button, still late. So that would be 0.4 times 0.1. That'd be late and no snooze. So 0.4 times 0.1. So for our final answer, the total probability that she's late to class, whether she hit the snooze or not, we add up those 2 outcomes. So 0.6 times 0.3 plus the 0.4 times 0.1. So total probability that she's late on any given random day would be 0.22. Part C says, suppose that Shannon is late for school. So we know she was late. What's the probability that she hit the snooze that morning? Seems like it'd be more likely that she hit the snooze if she actually showed up late to school. But we have to calculate exactly what's the probability she hit the snooze button that morning. And we know already that she was late. So we actually know that Shannon was late for school. So given that she was late to school, what's the probability that it was one of those mornings where she woke up and hit the snooze bar? So that's how we should read that. We're given that she was late. That's information that we know. So we know she was late. What's the probability she hit the snooze? It kind of makes sense that it's more likely that she hit the snooze if she was late, but we want to know because there's 2 ways that she could actually be late. What's the probability she hit the snooze and was late? Okay, before we start with our formula for conditional probability, maybe we should simplify these a bit. For example, 0.22 came from 0.6 times 0.3, which is 0.18, plus this 0.4 times 0.1, which was 0.04. So to calculate this, on our numerator, we want to know the specific case, the probability that she hit the snooze and she was late, so the 0.18. In the denominator, we have the total probability that she was late, whether it was hitting the snooze or not, the total probability that she was late. So that's how we're going to make our fraction here. So we know she was late to school. It just seems way more likely that she probably hit the snooze button. In fact, there's a 22% chance of her being late to school, right? So from that 0.22, 0.18 of it came from when she hits the snooze. Only 0.04 of it came from when she didn't hit the snooze. So if we know she's late to school, it seems more likely that she hit the snooze. So let's actually calculate that. The probability she hit the snooze and she was late would be that 0.18. The total probability that she was late would be the 0.22. So we have 0.18 over 0.22. So we have one specific case over the total, which gives us 0.818. Another way to say that, if we know she was late to school, there's almost an 82% chance that she hit the snooze button that morning. All right, let's go to example 4 here. False positives in drug testing. This is actually a big deal, and this happens. It says many employers require prospective employees to take a drug test. A positive result on this test indicates that the prospective employee uses illegal drugs. However, not all people who test positive actually use drugs. Suppose that 4% of prospective employees use drugs. The false positive rate is 5%, ouch. And the false negative rate is 10%. Part A says, what percent of prospective employees will test positive? So apparently there's two ways to test positive. You can actually be using drugs and you'll test positive, and that's true. Or you're not even using drugs, and for some reason the test is too sensitive and it thinks you're using drugs for some reason. You get a false positive. That's unfortunate. And apparently that happens 5% of the time. Definitely the easiest way to answer this question, what percent of prospective employees will test positive? Some of them will actually test positive and it'll be correct, and some of them will test positive and it'll be a false positive. It'll actually be incorrect. The best way to do this is definitely to draw a tree diagram. So let's start with our employees. At the end of the day, we just have our employees here at the beginning. And then our first case here, event 1 would be, of those employees, you have the ones that are using drugs and the ones that are not. And apparently it says 4% of employees actually use drugs. So we can figure this out. If 4% are using drugs, subtract that from 1, the leftover would be not using drugs. And unfortunately for those people not using drugs, there's still a 5% false positive rate. Ouch. And there could also be false negatives too. So whether or not you're using drugs, there's still people that would return a positive result or a negative result on this drug test. So our second event, we can go off this, would be a positive result on the drug test or a negative result. So we can just use plus sign or minus sign, positive or negative result. If you test positive, that indicates that you're on drugs. If you test negative, that indicates that you're not on drugs. So the false positive rate is 5%. Let's find out where we need to put that 0.05. A false positive, that's unfortunate. That would mean you're not on drugs, but for some reason you still tested positive. So that 0.05 should go right there. Not on drugs, but you got a positive. Okay, well then this branch should be easy to figure out. You're not on drugs and you tested negative. That'd be the leftover, that'd be 0.95. And then we have our false negative rate being 10%. So a false negative means you didn't test positive for drugs, but you should have. A false negative. So that would put 10% right here. On drugs, but tested negative. Okay? So the other branch, the missing piece here, on drugs but tested positive, that must be the leftover from the 10%, so that would be 0.9. Okay, so we've got our tree diagram. This thing just got a whole lot easier. What percent of prospective employees will test positive? So the probability that they test positive, whether it's true or not, how many or what percent will actually test positive in this case? Well, there's two different routes we could take. Either they're on drugs and they test positive, or they're not on drugs and they test positive, which is unfortunate, but apparently it happens in this test. So if I could map out these routes, drugs and positive, boom, 0.04 times 0.9, and then no drugs and positive would be 0.96 times 0.05. So 0.04 times 0.9, that's the first way to test positive. And the other route to test positive would be 0.96 times 0.05. Which gives us our total probability of a positive test to be 0.084, meaning there's about an 8.4% chance that an employee will test positive, whether it's right or wrong. So to summarize that number, 8.4% of prospective employees will test positive. And then part B, I think this is the more interesting question. It says, what percent of prospective employees who test positive actually use illegal drugs? So of that 8.4% of all the employees that tested positive, what percent of those actually use drugs? So let's start with, this is a conditional probability. Our condition is the employees who actually test positive. So given that you tested positive, what's the probability that you actually use drugs? So we know the probability, the total probability of employees testing positive. That's got to go in the denominator. That's our total probability of employees testing positive. That's 0.084. That's got to go in the denominator. And then the percent that use drugs and test positive, that's got to go in the numerator. So use drugs and test positive, that value has to go in the numerator. So we've got positive and drugs in the numerator, and then total positive in the denominator. So before we actually crunch those values, positive in drugs, that route was 0.04 times 0.9. And then the total positive, we know that's 0.084. Where'd that come from? Well, there was two cases, right? There was the 0.04, 0.9, right, plus the other way, which was false positives, employees not on drugs but testing positive. That was unfortunate. But there's still 0.96 times 0.05. So that gives us our total positive in the denominator, and we know that value is already going to be 0.084. So on top we got 0.036 divided by that 0.084, so we get 0.429. Meaning that in this case, there's a 42.9% chance that if you test positive on the drug test, you're actually using drugs. That seems rather unfortunate. It seems like they should fix their test to some degree, because of all the people that test positive, only 42.9% are actually using drugs in this case. So that seems like a really high rate of false positives. Maybe they could do something to adjust their test to lower that rate of false positives. Keep in mind, though, if you lower the rate of false positives, that usually increases the rate of false negatives. So there's got to be some sort of balance there. All right, and there's just a few pointers we got to finish off the notes with here. It says, what's the general multiplication rule? We went over that previously. That's the probability that A and B occur at the same time, the intersection. That should be the probability of A times the probability of B, given that A has occurred. Now, we wish it was just probability of A times the probability of B. And typically it is, but that can only happen for independent events, meaning the probability of B occurring, given that A has already occurred, B simply doesn't care that A has already occurred. So this would just be probability of B. Anyway, how does this relate to the conditional probability formula? So for conditional probability, we have the probability of B given A equals the intersection on top divided by the probability of A. That was our conditional event. How are these two related? And if you stare at this long enough, you might get it. Or maybe you already see it. So these actually are the same exact equation. They're just expressed differently. For example, if I take this equation right here and multiply by P of A on both sides, well, it would disappear over here and it would show up over there. So these formulas are actually the same, they're just expressed differently. Question 2, Q2. What's a very common way to lose AP credit on probability questions? So I'm going to go ahead and give this one to you. The answer is, if you don't show your work, right, you just throw a fraction out there with no work shown. And also, not providing the actual fraction answer. So if you just write 0.578, some weird decimal answer, that also is not enough. The graders are going to want to see where that fraction or where that decimal came from. So they're going to want to see the fraction as well. So two things, show your work and show the fraction. In fact, just leave your answer as a fraction. Oftentimes that'll work. But certainly just a decimal answer by itself is not good enough. And then the last piece here, when is it better to use a tree diagram than a two-way table? And what I've got is I just say multiple stages, or you have multiple rules that are occurring and they need to be combined. I'm definitely a fan of the tree diagram myself. Remember, it's about a sequence of events. So if you have event A occurring and then event B occurring and then event C, like if you have 3 layers of a tree, it's definitely better to try to represent it with a tree diagram than it is a two-way table. And to me, it's easier to organize visually through a tree diagram. So that concludes our discussion about conditional probability and tree diagrams for now. And that is it for these notes. I will see you in class.